So basically, our paper is Divergent Ensemble Networks. It is a novel architecture for uncertainty estimation. So uncertainty estimation, the major challenges that we face are that the time it takes for to calculate uncertainty during inference is a lot, because you need multiple outputs for predicting the uncertainty. So here our aim is to reduce that time during inference, and this network we propose for uh, time crucial activities. So basically, there are two types of uncertainties: aleatoric and epistemic. So aleatoric uncertainty is noise inherent in the data. We can't do anything about it, or unless we improve the sensors or something like that. But in 90% of the case, you can't do anything about aleatoric uncertainty. And epistemic uncertainty is when either the model doesn't have enough parameters to uh, model that function, or it doesn't have the data in all the regions that it needs to model. So the common methods that are generally used for modeling uncertainty are Monte Carlo dropout, ensemble methods, bootstrapping. There is also a Gaussian neural network, which is famous, but it is highly well known that it is way difficult to train. So we propose a new architecture called Divergent Ensemble Network. So I'll move directly to the architecture. So basically, there is an input layer. After that, there are few common layers, and it branches out like a tree. So our notion or the idea we came is from actually the tree itself. So if we give the same water through the roots, and if the leaves are different, that means the uncertainty is high. And if the leaves color are same, basically the uncertainty is less. So equivalently, if we provide the same input and we train these individual branches in a loop, like first we'll train the first branch, then the second branch, and iteratively we'll train the whole network. And if and similarly, we'll calculate either the variance or entropy or whatever measure that people use for uncertainty, and we'll decide. So the major trade-offs that we face in this model is that if suppose we want multiple outputs, like in the order of, let's say, 100, you want to be like super sure that the uncertainty is less, then this model faces that you will have to branch it a lot, and it might not be possible. It might be possible to use multiple such models, like in ensemble networks. So we tested this model on for classification as well as regression. For classification, we trained it on the MNIST dataset, which is the very famous dataset where there are numbers labeled from 0 to 9, and we inferenced it on non-MNIST dataset, which contains A to J letters as well. So on the letters, it should show that the variance in the output should be high. And for regression, we took a toy regression function of 10 sin x plus epsilon being the noise. And for training it, we sampled it between -3 and 3, and we inferenced it on the region outside -3 and 3. So that is 3 to infinity in the positive side, and -3 to negative infinity in the negative side. So uh, we compared these results with Monte Carlo dropout, deep ensemble, and bootstrapping. So I won't directly point out the results here. It would take a lot of time. But the main pointer I would like to say that rest of the scores are approximately, you will get a plus minus 1% difference. But the inference time of our model here, as you can see, is average inference time is 0.05 compared to ensemble, which is in 0.2, Monte Carlo in 0.1, and bootstrapping in 0.2. Similarly, for the not MNIST during inference time, the inference time is almost one-fourth, or it is sometimes 6 times faster than the normal models. These are the results for the regression dataset. Here you can see the similar results. So the key insights that we gain from this model is that it comparatively performs very well in real world scenarios where you need real time uncertainty estimation, and its accuracy is also pretty well. You can see that our model's accuracy for the MNIST data set is 98.78, which is highest among the other three that we compared it with. And even the average variance is second highest among the ones which we compare it with. So future directions is that here we didn't concentrate much on how to optimize this, and we didn't test it on a larger data set. MNIST only has 70,000 images of 28 or 32 cross 32. So these are the future works that we propose. In conclusion, basically, it just provides faster uncertainty for real time work. Thank you.